In this video, we're going to talk about a concept known as the common ion effect. The name is pretty self-explanatory. We essentially stress a system in equilibrium by adding a common ion, or we add a salt to a system that already has a common ion, and as such, the equilibrium is going to respond accordingly. So we talk about this in terms of solubility and acid-base equilibrium. So here we have a typical solubility question, and first of all we're just going to think about what happens when we add some sodium chloride to silver chloride. There's silver chloride as ionization, and there's sodium chloride as an ionacing, both of which are aqueous. So we've added chloride ion, so we've increased the chloride ion concentration. So we can predict based on Le Chatelier's principle what's going to happen here because of the increased concentration of chloride ion. And it's going to shift left towards the reactant silver chloride and produce more solid. As a consequence, this would be viewed as a decrease in molar solubility. So here it is explained a little bit. If you like, you can pause the video and have a bit of a read, but essentially it just goes over the same process we just looked at. Le Chatelier's principle allows us to predict what will happen by stressing our equilibrium. In this case, the stress is an increase in chloride ion concentration. That means there is a shift left. Shift left is a decrease in the molar solubility. There's less in solution. So, another example. First of all, calculate the molar solubility of PbCl2 with a KSP of 1.7 times 10 to the negative 5. An ionization expression is useful. You obviously need a KSP expression. Concentration of Pb2 plus times the concentration of Cl minus squared, and then you simply plug in your variables and you come to the value 0.16 moles per liter is the solubility of PbCl2 at this temperature, whatever it may be. So what happens if we add a common ion, namely chloride ion, by putting our PbCl2 in a solution containing NaCl? Here's where an ice table is useful because it gives us our 0.10 plus 2x expression at equilibrium for the common ion that is present. Common ion again is chloride ion. We have our Pb2 plus and chloride ion. Because we have initial concentration of Cl minus, we now have at equilibrium 0.10 plus 2x. We can make the assumption, which simplifies this problem. It's a pretty low KSP and it's a fairly high concentration. And so at equilibrium, the molar solubility 0.0017 moles per liter. That is less than it was for PbCl2 without the common ion, and that should make sense. It is predictable. What if we have a different common ion? What about Pb2 plus instead of Cl minus? What's going to be the effect? Well, we would predict the same effect. The molar solubility should go down because we've added a common ion. There it is, Pb2 plus. We can still make the assumption because the KSP has not changed, nor has the concentration. And when we go through the process, we come up with a molar solubility of 0.0065 moles per liter, which also decreases and which is also predictable. So there's the summary. Molar solubility 0.016 for PbCl2 decreases in the presence of both chloride ion and Pb2 plus ion, but not to the same extent. And the reason for that is, again, the stoichiometry involved in the KSP expression.